Section 8.7, L'Hopital's rule. Well, we've been dealing with derivatives, which are slopes, and specifically the derivatives are limits as we approach a certain x value. So, because we're dealing with an instantaneous rate of change. Limits help us predict y values that are hard to determine, but sometimes the numerator and denominator send mixed messages about the behavior of the function. How can we make sense of this and send a clear message about the function's intended y value? For the function f of x equals x squared, what is happening to the y values as x approaches infinity? So this is just a parabola, right, at the origin. So as x is approaching infinity, what is happening to the y? As x approaches infinity, well, f of x is going up, so it's also approaching infinity. We can also write this as the limit as x approaches infinity of f of x equals infinity. Next, for the function g of x equals the natural log of x, what is happening to the y values as x approaches infinity? This is not quite as familiar a graph, but remember this graph goes like this, right? So what's happening as x approaches infinity to this graph? Well, it's going out this way, right? But it's still going up. So as x goes to infinity, f of x is also going to infinity. So we can write this one the exact same way. The limit as x approaches infinity of f of x is infinity. Well then, which function, f of x or g of x, is growing at a faster rate? And how do you know? So think about that, pause the video, and write down your answer. So what do you think? Which one is growing faster? If you look at the graphs even, which one is growing faster? So hopefully you already wrote down that f of x is growing faster, at a faster rate, because the slopes of f of x are getting steeper, whereas the slopes of g of x are getting flatter. They're both getting bigger, but the g of x is getting bigger at a much slower. Now let's go ahead and evaluate the limit as x approaches infinity of the natural log of x over x squared. Well, we just determined up above that if we actually plug in infinity, or a number really large, we're going to get infinity over infinity. But what do you think the limit is actually going to go towards? Again, pause the video and think about it and write it down. Well, if you think about this kind of the way we were thinking about things back in Algebra 2, the denominator, x squared, is getting fairly large fairly fast, whereas the numerator is just kind of leveling off. Therefore, the ratio of the numerator to the denominator is much bigger than the numerator. Therefore, the function is actually approaching 0. You could actually put the function natural log of x divided by x squared into your graphing calculator and kind of verify that. All right, moving on to number 5. Let f of x be x squared plus 2x minus 15, and g of x equals x minus 3. So the first thing we're going to just do is evaluate f of 3 and evaluate g of 3. No derivatives, just the function. Go ahead and pause the video and do that. So f of 3 is 0 and g of 3 is 0. So why does direct substitution not work to evaluate the limit of f of x over g of x as x approaches 3? And hopefully it's fairly obvious for you to see, is because you would get 0 over 0, and that again is an indeterminate form. But that's okay, we can deal with an indeterminate form. We did this back in chapter 2 when we were first learning about limits, and so we're going to use the factoring method to evaluate this. Go ahead and factor the numerator, and then see if from there you remember what to do to evaluate this limit, and see if you can finish this problem. So when we factor the numerator, we get that, and then conveniently, x minus 3 cancels, so we're taking the limit as x approaches 3 of x plus 5. When we plug that in, we get 8. So I've just rewritten those equations at the top of this page, the functions, but now we're going to look at this limit from a different perspective. How do the values of f of x and g of x at x equals 3 compare? Well, we just figured that out, right? They're the same. F of 3 equals g of 3 equals 0. Well, now let's see which function, f of x or g of x, is changing at a faster rate at x equals 3. How do you know? Again, Pause the video, see if you can answer that, and if you can figure out how to answer that, then go ahead and do that. Hopefully you recognized or realized that we're talking about a faster rate, so all we need to do is compare the slopes at x equals 3, which means we need to take the derivative. And when we take the derivative, we can see that f is changing at a faster rate because the slope of the g function is a constant rate of 1, whereas the f function has a slope of 2, so it is going to be increasing. So f function is changing faster. What that means is that when we're comparing our y values, if we end up with an indeterminate form and we can't determine where what is happening with that function at that value, then we can compare the growth rates of the function. So let's kind of formalize that. In number 7, let's evaluate the limit as x approaches 3 of f prime of g over g prime of g. Again, pause the video and go ahead and do this. Note you're not doing the quotient rule. You're simply taking the derivative of the numerator, the f function, and you're leaving the derivative of the denominator on the bottom. There's just the problem written out, the limit as x approaches 3 of f prime of x, 2x plus 2, over g prime of x, which is 1. Now we're just going to find that limit, so we're going to do direct substitution. Using our direct substitution, we get 8, and hopefully you remember that just a few minutes ago, in number 5, when we did the factoring method to solve this limit, we also got 8. When do you think comparing growth rates is a helpful strategy for evaluating limits? Well, basically, when the direct substitution gives an indeterminate form, right? We could do the factoring method, and we can do that, or we can use, this is called L'Hopital's rule. And the indeterminate forms we're talking about is 0 over 0, or plus or minus infinity over plus or minus infinity. So now let's talk about those important ideas of L'Hopital's rule. First of all, this only works basically when you are dealing with a rational function. So limits resulting in 0 over 0 or plus or minus infinity over plus or minus infinity are considered indeterminate. If you get one of those forms, then we're going to consider the ratio of the growth rates instead, and this is called L'Hopital's rule, which states if the limit as x approaches a of f of x over g of x is indeterminate, then you can evaluate the limit as x approaches a of f prime of x over g prime of x. And also make a note that this is not the quotient rule. If the result is still indeterminate, repeat the process and finding another derivative of the top and the bottom. All right, let's do a few problems. The limit as x approaches 0 of e to the x minus 1 over sine of x. E to the x to the 0 is 1 minus 1. We get 0 over sine of 0 is 0. So we have to use L'Hopital's rule. The limit as x approaches 0, we're going to take the derivative. Derivative of e to the x is e to the x. Minus 1 would be 0. Derivative of the sine of x is the cosine of x. Now we can use direct substitution, and e to the 0 over the cosine of 0. E to the 0 is 1. The cosine of 0 is 1, so we get a limit of 1. Go ahead and pause the video and try number 2 and 3, please. Checking direct substitution first, you do get 0 over 0, so now we have to use L'Hopital's rule. Derivative of the top, 2x plus 10, over the derivative of the bottom, which is 2x, and now we can use direct substitution. And you should get a positive 2/7 for that one. Now let's go ahead and try number 3. So again, I checked that initially I got 0 over 0 and I couldn't use direct substitution, so I took the derivative. I got 12x squared minus 12x over negative 10x. If I use direct substitution, I still get 0 over 0. So I have to use L'Hopital's rule a second time. And when I do this time, if I use direct substitution, 24 times 0 is 0, so I get negative 12 over negative 10, which simplifies to a positive 6/5. Selected values of differentiable functions f, g, f prime, and g prime are given in the table below. Evaluate that limit. Again, try direct substitution first. We do get 0, 0, so we do have to use L'Hopital's rule. But I do want to caution you before you pause the video and do this on your own. take a second to look at what you have to do, hopefully you recognize that you do need to use the product rule on the numerator. You have x times f of x. So pause the video and go ahead and try number 4. So doing the product rule, we have 1 prime 2 plus 2 prime 1. And then remember that the minus 6, the derivative of a constant, and on the denominator of the 1, those are both 0. So now just go ahead and substitute in, just do direct substitution now that we've found the derivative. And you should get negative 5/2. All right, when we do the last one, the limit as x approaches infinity, well, we have a parabola on the top and a parabola on the bottom and x squared, so these are both going to go to infinity over infinity. Again, we have to use L'Hopital's rule, so please go ahead and do that and check back. Applying L'Hopital's rule, we have 6x minus 7 over 10x, and still, as x approaches infinity, we're going to get infinity over infinity. So we have to apply L'Hopital's rule again. We're going to get the limit as x approaches infinity of 6 over 10, directly substituting in, well, there are no x's, so we get, simplifying this, we get our 3/5. That is all the notes for this section. In fact, that is all the notes until you will take your test. So please come to class with questions on this or anything else from this chapter that you'll be tested on.